Search a 2D matrix. If you can spot hidden structure, you win interviews. Search a 2D matrix disguises a sorted array inside a grid and tests whether you can binary search it without flattening anything in memory. This Pattern Mastery 100 Classic Filters for Pointer Precision and Index Math. Let's solve it with basics so you can explain it cleanly and code it fast in O of log of m times n. Breakdown. We're given an m by n matrix where each row is sorted in ascending order. The first element of each row is greater than the last element of the previous row. That structure means the matrix behaves exactly like one long sorted array of length m times n when read row by row. Given a target, we return true if it exists and false otherwise. Assess. A naive scan is O of m times n, but because the matrix is globally sorted, we can run a standard binary search in O of log of m times n with O of 1 extra space. The key trick is mapping between dimensions. Row equals mid divided by n, using integer division. Col equals mid modulo n. Or using Python's built-in, row, col equals dov mod mid, n. Structure. The plan is straightforward. Guard against empty inputs, set left to 0 and right to m times n minus 1, while left is less than or equal to right. Compute mid. Convert mid into row and column. Compare matrix at row and column to the target. If it matches, return true. If the midpoint value is smaller, move left to mid plus 1. Otherwise, move right to mid minus 1. If the loop ends with no match, return false.
Let's try to implement it using solution 1. We begin by defining a class named solution, which simply organizes our function. This sets up our search matrix function, which receives a 2D list called matrix and a value called target that we want to locate somewhere inside it. This line checks whether the matrix is empty, or whether the first row is empty. If either is true, there is nothing to search. So if the matrix has no data, we immediately return false, because the target cannot be present. We store the number of rows in M and the number of columns in N. This helps us translate between a 1D index and a 2D position later. We set up two pointers for binary search. L starts at index 0. R starts at the last index of a flattened version of the matrix, which is total elements minus 1. This lets us pretend the matrix is one long sorted array. The binary search begins. We continue as long as the left index has not passed the right. Since we have the search range each step, the time complexity is O of log of m times n. We compute the middle index in our imaginary 1D list. This midpoint is where we will check next. This clever line converts the 1D midpoint index back into a 2D row and column. Mid divided by n, using integer division, gives us the row. Mid modulo n gives us the column. Val is the actual number stored at that spot in the matrix. We check whether the value at the midpoint is exactly the target. If it is, we have found the target and return true right away. If the midpoint value is smaller than the target, then the target must be further to the right in our virtual list. So we shift the left pointer to just after the midpoint. This covers the case where the midpoint value is larger than the target. We move the right pointer left to search the earlier half of the list. If the loop ends without finding the target, we return false, meaning the value does not exist in the matrix. And that's how this algorithm works. It first checks that the matrix is valid, then treats the entire 2D grid as one sorted list and uses binary search to test middle positions until the target is found or ruled out. Efficient, simple, and elegant. Check. Let's walk through this test case for the search a 2D matrix problem and confirm why the output is true. Input is matrix equals 1, 3, 5, 7, 10, 11, 16, 20, 23, 30, 34, 60. Target equals 3. Here's what the input means. Matrix is a 2D grid where each row is sorted in ascending order. The first element of each row is greater than the last element of the previous row. Target equals 3 is the value we want to check for inside this matrix. The problem usually treats this structure almost like a flattened sorted array, so we can use binary search logic. Why the output is true. Let's inspect the matrix row by row. Row 0, 1, 3, 5, 7. Row 1, 10, 11, 16, 20. Row 2, 23, 30, 34, 60. The target is 3, and we can see. It appears in row 0, at column 1, matrix at row 0 column 1 equals 3. Whether the implementation first finds the correct row, because 3 lies between 1 and 7, and then searches inside that row, or treats the whole thing as a single sorted list and binary searches directly. It will eventually land on this element and return true. The output is true, and the expected value is also true, which confirms the search logic is correctly locating the target inside the 2D matrix. Now let's try another implement approach using solution 2. We start by defining a class named solution, which simply groups our function. This sets up our search matrix function, which receives a 2D matrix and the value we're searching for. This line checks whether the matrix is empty or whether the first row is empty. If the matrix has no data, we immediately return false. The target cannot be found. We store the number of rows in M and the number of columns in N, giving us the full dimensions of the grid. We set up 2 pointers to perform a binary search over the rows. Top starts at the first row. Bottom starts at the last row. We initialize a variable called row to store which row the target might be in. A value of -1 means we have not found that row yet. We begin a binary search on the rows. This loop runs in O of log m time. We compute the middle row index to check next. If the target is smaller than the first element of this middle row, then it must be somewhere above this row. So we move the bottom pointer upward. If the target is larger than the last element of the middle row, then it must be below this row. We move the top pointer downward to search lower rows. If the target is not too small or too large for this row, it means the target could be in this row. We store this row index. This is the only row where the target could possibly exist, and we stop the raw search. If the raw search ended without finding any valid row, we return false, because the target cannot be anywhere in this matrix. Now we set up a second binary search, this time within the identified row, using column pointers. This begins the column-level binary search, which runs in O of log n time. We calculate the midpoint column. If the value in the middle column equals the target, we have found it and return true right away. If the midpoint value is smaller than the target, we look to the right half. We move the left pointer to narrow our search to columns on the right. This means the midpoint value is larger than the target, so we move the right pointer leftward to search earlier columns. If the loop ends without finding the target, we return false. It is not in this row. And that's how this algorithm works. It first locates the only possible row using a binary search across the row range, then runs a second binary search inside that row to pinpoint the target. Efficient, simple, and elegant. Check. Let's verify this test case for the search a 2D matrix problem and see why the output is false. Input is matrix equals 1, 3, 5, 7, 10, 11, 16, 20, 23, 30, 34, 60. Target equals 13. What the matrix structure tells us. Each row is sorted. The first element of each row is larger than the last element of the previous row. The entire matrix behaves like one long sorted list. Our goal is to determine whether 13 appears anywhere inside this structure. Why the output is false. Let's scan logically. Row 0, 1, 3, 5, 7, 13 is greater than all of these. Row 1, 10, 11, 16, 20. 13 lies between 11 and 16, but it is not equal to any element in this row. Row 2, 23, 30, 34, 60. 13 is less than all of these. Since 13 does not match any number in any row, the binary search, or this row and column search, never finds a match and never returns true. Thus, the correct result is false. The output false matches the expected false, confirming the function correctly determines that the target 13 does not exist in the matrix.
Let's have a quick recap. Breakdown recap. So, wrapping up, search a 2D matrix is all about recognizing structure. You're given a matrix where each row is sorted, and every next row starts higher than the last one. Conceptually, that means the entire matrix behaves like one long sorted array. The challenge is to find the target efficiently, without actually flattening the data. Assess recap. We looked at our options. A brute force scan checks every element in O of m times n, but that's wasteful. Because the matrix is globally sorted, we can treat it as a single sorted list and use binary search. That drops the time down to O of log of m times n, while keeping space constant. The key was mapping a 1D index back to 2D coordinates using simple math. Structure recap. The logic was straightforward. Set up 2 pointers, left at 0 and right at m times n minus 1, and repeatedly check the middle index. Convert that index into a row and column, compare the value to the target, and adjust boundaries until you find it or the range collapses. Implement recap. During implementation, we guarded against empty input, then built a clean binary search loop. Each step calculated mid, mapped it to row and column, and compared the value. The solution stayed compact, efficient, and easy to follow. Check recap. When we ran through multiple test cases, every result matched perfectly. The function correctly returned true for existing values and false for values that were missing. All outputs confirmed the O of log of m times n performance and flawless index mapping. The big takeaway? When problems look multidimensional, look for patterns that reduce them to one dimension. Spotting hidden order is a key interview skill, and mastering that mindset turns complex grid challenges into elegant binary search solutions.